Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
This is Andrew and Renee. Welcome to the Stack series.
Today we are exploring the nature of time specifically, whether it actually flows or if that is just a persistent illusion.
And it really is. I mean, it's probably the most fundamental experience we have as humans, isn't it?
It has to be. You wake up, the day progresses, you go to sleep. It feels, well, it feels like a one-way street.
Completely. It's a linear progression. We feel it in our bones.
It feels like a river. That's always the go-to metaphor, right? Time is this powerful current just carrying us forward.
Right. From a past that's already happened, that's set in stone.
And through the present moment, which feels like the only thing that's truly real.
On its way to a future that, hasn't been written yet.
Exactly. That's the common sense view. That's how it feels.
It's the manifest image of the world, for sure. But what if I told you that in the fundamental equations of physics, that river, it just isn't there?
I would say you might need a new watch. I mean, I'm pretty sure we're moving forward in time right this second. It feels very real to me.
Oh, I'm sure it does. But the source material we've pulled for today's discussion, I mean, it's a massive stack. We're looking at everything from Einstein's relativity all the way to Julian Barber's really radical book, The End of Time.
I saw that one in the stack. The title alone is provocative.
It is. And when you put it all together with, modern quantum experiments, that whole picture of time as a river, it starts to, just sort of evaporate.
Evaporates. That's a strong word.
I think it's the right one. We might not be in a river at all. We might be living inside a static block of ice where the future is just as real and solid as the past.
Okay, hold on. A block of ice.
Or maybe time is something that emerges, like steam rising from a hot cup of tea. It's not a fundamental thing, but a consequence of something else.
Like heat?
Like heat.
Oh.
Or it might even be a hologram projected from the edge of the universe.
A hologram. Okay, that's a slightly terrifying thought to kick things off with. The idea that now isn't special, that my future is already out there, just sitting on a shelf waiting for me.
It's deeply counterintuitive. I get it.
It goes against every single instinct my brain has. My brain is screaming that this conversation is happening now, and 5 minutes from now hasn't happened yet.
It is. And that's why this is going to be such a fascinating exploration. We're not just, summarizing a few papers here. The goal is to really try and dismantle your perception of reality.
Just casually dismantle my entire reality. No big deal.
And then rebuild it using what modern physics is telling us.
All right. I'm ready. A little nervous, but ready. How are we going to tackle a topic this massive?
We've got a good structure planned out. It'll take us from the, let's say, solid ground of classical physics right into the really weird quantum fog.
Right.
So first, we'll cover the foundations. This is what we think we know. We'll talk about that block universe concept and why Einstein, for all intents and purposes, killed the idea of a universal now.
Right, the block of ice.
Exactly. Then we dive straight into the active debate. And this is where science is really at odds with itself.
The messy part.
The very messy part. It's a huge clash between quantum mechanics and gravity, and it leads to something called the problem of time, where time literally just drops out of the mathematics.
It just vanishes
Yeah.
from the equations describing the universe.
Oof. Gone. It's a huge problem.
Wow.
After that, we'll look at the frontiers. This is the really mind-bending stuff. We'll explore how time might emerge from quantum entanglement or, get this, even from our own ignorance.
Time comes from ignorance. I should have a lot of it then.
We all do, apparently. And finally, we have to talk about the implications.
This is the so what part.
Absolutely. Because if the future already exists, I really need to know if I have free will. And I also want to know why my brain is so convincingly lying to me about this whole flow of time.
Yes. Ethics, neuroscience, how to live your life in a universe that might be timeless. That's where the rubber meets the road. All right, let's do it. Let's jump into the foundation. Start with that feeling, that river.
Okay, so in philosophy, that intuitive view has a name. It's called presentism.
Presentism.
Mm-hmm.
It sounds like something you'd practice in a mindfulness class.
It could be, but it's really just the common sense view that only the now is real, the present moment.
So the past is just a memory, something that's gone.
Gone forever. And the future is just a possibility, a fantasy. It hasn't happened. Reality is that razor's edge of the present moment we're experiencing right now.
Right. That's how I operate. That's how we all plan our days. The past is done with. It's It's non-existent in a physical sense.
But physics, and specifically Einstein's general relativity, it gave us a completely different model. It's called Eternalism. But most people know it as the block universe.
The block universe. I've heard the term so many times, but I want to nail it down. What does it actually mean? It makes me picture us all being trapped inside a giant cube.
That's not too far off, actually, but it's a bit more profound. Let's use an analogy. Imagine a loaf of bread.
Okay, a loaf of sourdough. Let's make it a good one.
Perfect. In this analogy, the entire universe, everything, all of space and all of time from beginning to end, is that loaf of bread.
The whole thing.
The whole thing. One heel of the loaf is the Big Bang.
The beginning.
And the other heel, way at the other end, is the heat death of the universe, or whatever the ultimate end is.
And the crucial part is that the whole loaf exists at once. It's just sitting there.
Yes. The loaf is sitting on the kitchen table. It is a complete static object. Now, the important question is, where are you in that loaf?
Well, I guess I'm a slice, right? Me, right now, having this conversation, that's one very thin slice somewhere in the middle of the loaf.
Exactly. You're a slice.
Yeah.
But here is the absolute key concept of the block universe. Just because you were standing at one coordinate, let's call it slice number 50, that doesn't mean slice number 1 or slice number 100. Doesn't exist.
They're just somewhere else in the loaf. They're not my slice.
Precisely. In the block universe model, the past, the present, and the future all exist simultaneously in a single four-dimensional block. There's no special now that's moving through the block. Now is just your coordinate. It's no different from here.
Okay, let's pause on that, because that's a huge shift. We treat here and now so differently in our language and our thinking.
We do.
If I say I'm in New York, I know for a fact that Boston exists. I'm just not there. But if I say I'm in the year 2026, my deep-seated assumption is that the year 2027 doesn't exist yet.
And that is the exact distinction that Einstein's physics erases. In the block universe, you can't say the past doesn't exist just because you happen to be in the present.
Any more than I can say Boston doesn't exist just because I'm in New York.
Exactly. The dinosaurs are still roaming the earth in their slice of the loaf, and your great-great-grandchildren might be flying starships in their slice. Both of those moments are just as real as this one.
That makes me feel incredibly small. And honestly, a little claustrophobic. If the future's already there, it really does feel like the script is already written.
We are definitely going to get to the strip part later. But first, it's really important to understand why physics felt it needed this block model. Why couldn't we just stick with our nice, comfortable river? Why did Einstein have to come along and freeze the whole universe?
Yeah, who gave him permission to turn our universe into a loaf of bread?
It all comes down to a concept called the relativity of simultaneity. This is the mechanism that really breaks presentism, that only now is real idea.
And this is the idea that what you consider now depends on how fast you're moving.
That's the one. And to really get it, we have to visualize this slice of now. So imagine the universe is that loaf of bread again.
Right.
If you and I are sitting still next to each other, we're slicing the bread straight down, perfectly perpendicular to the crust.
Got it. A straight vertical cut. So my knife hits Earth and, say, the Andromeda Galaxy at the exact same moment in time.
Yes. That is our shared now. We agree on what is happening everywhere in the universe at this very instant. But here's the twist Einstein discovered. Your velocity changes the angle of your knife.
The angle of my knife.
Yes. If you start moving relative to me, even just a little bit, you're no longer slicing straight down. Your knife tilts. Your definition of what is simultaneous across the universe tilts along with it.
Okay, but how much of an angle are we talking about? If I get up and walk across the room, surely it's not a big deal.
At human speeds, it's infinitesimal. You're right. If you walk across the room, your knife tilts by a tiny, tiny fraction of a degree. The difference between my now and your now would be nanoseconds. It's completely unnoticeable.
Because we're close to each other and we're moving incredibly slowly compared to the speed of light.
Right. But this is where the geometry gets absolutely wild. This is something called the Rietdijk-Putnam argument, but it's often illustrated with the Andromeda Paradox.
The Andromeda Paradox.
Imagine that laser pointer, your knife, extends all the way from here to the Andromeda Galaxy. That's about 2.5 million light years away.
That is a very, very long knife.
It is. Now, think back to basic geometry class. If you have a lever that's millions of light years long, and you move the handle by even a billionth of a degree, what happens at the other end?
The tip of the lever moves a massive distance. A tiny shift here translates into a huge swing way out there.
Precisely. So let's say there's an alien in the Andromeda galaxy. If that alien simply gets up from their chair and starts walking towards Earth at a casual walking pace, maybe 4 kilometers an hour,
Okay.
that tiny velocity is enough to tilt their plane of simultaneity. And because Andromeda is so ridiculously far away, that slice of now swings wildly through Earth's time.
You keep saying wildly. What are we talking about here? Minutes?
Yes.
Hours?
We're talking days, possibly even weeks. Depending on the exact speed and distance, that alien's now slice doesn't cut through Earth today. It cuts through Earth next Tuesday.
Hold on. Wait a second. So in that alien's definition of the present moment, the me of next Tuesday is already doing whatever it is I'm going to be doing.
Yes. That event, you spilling coffee on your shirt next Tuesday, is on their simultaneous slice of the universe. To them, it is happening now.
But I haven't done it yet. I'm sitting right here.
You haven't done it yet in your slice. But for the alien moving towards you, it's present tense. And it gets weirder. If they turn around and start walking away from Earth...
The angle of the knife tilts the other way.
Right. And their now swings back in the other direction. It could slice through Earth's timeline last week.
This implies that next Tuesday and last week have to be physically real places that you can just point to if you have a long enough stick and you're moving the right way.
That is the inescapable conclusion of relativity. If you accept that the alien's perspective is just as valid as yours, and that's the whole point of relativity, there's no privileged observer, then you have to accept that your future is just as real as your present. It has to be there waiting to be observed.
So if you and I can't even agree on what now is across the universe, then you can't claim that now is the only thing that exists.
You can't have a universal now if everyone is cutting the loaf at a different angle.
Therefore, the whole loaf must exist. The past, the present, the future. It's all just there.
The future is just as fixed as the past.
Okay, my brain is definitely hurting, but I am following the logic. The block universe is the only way to reconcile everyone's different perspectives.
Yeah.
But Renee, if the whole block is just sitting there, completely frozen,
Yeah.
why does it feel like we're moving through it?
Yes. The million-dollar question.
If I'm just a coordinate in a static block, why do I experience this flow? And more importantly, why do I remember the past but not the future? If the future is just as real, why can't I remember it?
That brings us to the next piece of the puzzle, the arrow of time. And for this, we have to step away from relativity for a moment and talk about thermodynamics.
Thermodynamics. Okay, so we're talking about heat and energy.
We're talking about entropy, specifically. See, if you look at most of the fundamental laws of physics, like Newton's laws of motion, or even Schrödinger's equation in quantum mechanics, they're mostly time-symmetric.
Meaning what exactly? Time symmetric.
It means the laws don't care which way the movie is playing. If you took a video of the planets orbiting the sun and played it backward, it would look perfectly natural. The physics works just as well in reverse. There's no inherent forward or backward in the base equations.
But if I take a video of me dropping an egg on the floor and play that backwards.
Right. Let's really visualize that. You drop an egg, it hits the floor, it shatters. Yolk and shell everywhere. It's a mess. Now, rewind the footage.
I see a puddle of goo on the floor spontaneously rise up. The yolk and shell fragments fly together, the shell seals itself perfectly, and the whole egg leaps up off the floor and lands in my hand.
And you know instantly, without a shadow of a doubt, that the film is being played in reverse.
Of course, because that just never, ever happens.
But here's the absolute kicker, Andrew. It could happen.
No, it couldn't. An egg can't unbreak itself.
According to the fundamental laws of motion, it is theoretically possible. All of those trillions of atoms in the yolk and the shell, if they were all just bumped by air molecules in the exact right way with the exact right amount of energy, they could reverse their trajectories and perfectly reassemble. There is no fundamental law of physics forbidding it.
So, why don't we ever see it happen? Not even once.
Because it is statistically, astronomically, impossibly unlikely. And this is the core of the second law of thermodynamics. It's all about probability. It introduces the concept of entropy.
Disorder. That's the word that always comes to mind.
It's often described as disorder, yes, but it's actually more precise to think of it as the number of ways a system can be arranged. Probability.
Okay, explain that.
There is only one way for the egg to be whole and sitting in your hand, or, very few ways. That's a low entropy state.
Yeah.
It's highly ordered and specific.
Right, very particular arrangement of atoms.
But how many ways can the egg be broken and splattered on the floor?
Trillions upon trillions. The yolk could be here, a shell fragment could be over there. It's a mess.
It's a high entropy state. So as systems evolve, They naturally tend to move from states with very few possible arrangements, order, to states with a huge number of possible arrangements, disorder.
And not because there's some force pushing them towards being messy?
No, that's the key. It's just because there are vastly more ways to be messy than there are to be tidy. It's simple statistics.
I think we have that visualization in the source notes, the one with the particles in a bottle.
Yes, that's a perfect illustration. Imagine you open a bottle of perfume in a sealed room. At first, all the perfume molecules are trapped inside the bottle. They're ordered, their location is very specific, low entropy.
Okay.
Now you take the cap off. Over time, the molecules bounce around randomly and spread out into the room.
They diffuse. The whole room starts to smell like the perfume.
Eventually, they're more or less evenly distributed throughout the entire room. That's the high entropy state. Now ask yourself, what are the odds that all of those molecules will, just by chance, all bounce their way back into that tiny bottle at the exact same time?
Effectively zero. You'd have to wait for billions of years, probably longer than the age of the universe.
Exactly. And that transition from the bottle to the room, from the whole egg to the broken egg, that one-way street of probability gives us the arrow of time.
So we feel time flowing forward because we are riding this unstoppable wave of increasing entropy. We're just constantly moving from a more ordered state to a less ordered one.
From the very ordered bottle state of the Big Bang towards the much messier, empty room state of the future.
So time isn't a force pushing us along. It's just this statistical likelihood of things getting more jumbled up.
In the thermodynamic view, that's exactly right. The physicist Ludwig Boltzmann, who was a pioneer in this field, he basically suggested that the past is nothing more than the direction in which entropy was lower.
That's a weirdly bleak but very logical way to look at it. So, to recap, we have the block universe from relativity, which says the entire stage, past and future, is already built.
Stage is set.
And we have the arrow of time from entropy, which explains why we all walk across that stage in only one direction. It seems like a pretty complete picture. Case closed.
Oh, if only it were that simple. We are just getting started.
I had a feeling you were going to say that.
Because while relativity is very happy with its block universe and thermodynamics is happy with its arrow of time, quantum mechanics shows up and has a major bone to pick with the entire concept.
Of course it does. I knew quantum mechanics would ruin the party. It always complicates things.
It's its specialty.
Yeah.
And this brings us right into the active debate section. This is where modern physics is currently stuck.
So what's the problem?
The problem is we have two foundational theories of the universe. General relativity, which is brilliant at describing the big stuff stars, galaxies, gravity, the warping of time, and quantum mechanics, which is brilliant at describing the small stuff atoms, electrons, particles.
And they just don't get along.
They despise each other. And their biggest point of disagreement is on the very nature of what time is.
How can they disagree on something so fundamental?
In general relativity, Einstein's world, time is dynamic. It's a player in the game. It can stretch. It can shrink. It gets warped by gravity near a black hole. It's part of the very fabric of space-time.
It's the coordinate we talked about. It's part of the loaf of bread.
Exactly. But in standard quantum mechanics, time is, well, it's boring. It's just a rigid background clock. It just marches on, tick, 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 the same for everyone, everywhere. It's not affected by what the particles are doing. It's just a parameter in the equations, not a physical thing.
So one theory says time is a flexible, interactive fabric, and the other says time is a rigid, absolute ruler.
You've nailed it. And that causes an absolute disaster when you try to combine the two theories to create a theory of quantum gravity. This is what's known as the problem of time.
So what happens when you try to merge them? When these two ideas crash into each other?
Time vanishes.
It just goes away.
Let's talk about the Wheeler-DeWitt equation. This is a very famous piece of mathematics from the 1960s. Two physicists, John Wheeler and Bryce DeWitt, they tried to write the master equation for the entire universe.
The theory of everything.
That was the goal. They tried to combine quantum mechanics and gravity, and they derived this beautiful equation that was supposed to describe the quantum state of the whole cosmos. They wrote it out, they double-checked the math, and they stared at it in what I can only imagine was horror.
Why? What did the equation show them?
Or, more accurately, what it didn't show them. Andrew, you remember from science class, whenever we describe how things change, we're always looking for the time variable. We're looking for t, the rate of change over time.
Right. Velocity is distance over time. Acceleration is change in velocity over time. Everything in physics is something per second.
The Wheeler-DeWitt equation has no t. The time variable is completely absent. On one side of the equal sign is an operator representing the whole universe, and on the other side is just zero. H psi equals zero.
Zero.
Zero. Which means the rate of change of the universe, according to this equation, is zero.
Wait, hang on a second. If the rate of change of something is zero, that means it's not changing.
Correct.
It means nothing is happening.
That's what the math implies.
But things are happening. I'm talking you're nodding, the Earth is spinning. How can the most fundamental equation of the universe possibly say that nothing is happening?
That is the problem of time. The math is robust, the derivation is sound, but it predicts a universe that is a frozen static crystal, a block. It suggests that at the most fundamental level, the universe is timeless.
So either the math is profoundly wrong, or my entire experience of reality of things changing is a complete and total hallucination.
Or maybe change itself isn't what we think it is. And this leads us directly to the work of a physicist named Julian Barbour. He's a fascinating figure who looked at that zero and basically said, maybe the math is telling us the truth. Maybe time really doesn't exist.
I was reading through some of his work in our source stack. He literally wrote a book called The End of Time. He's not messing around with that title.
He takes the problem of time more seriously than almost anyone. He argues that time is not real. There is no invisible river. Instead, he says the universe is just a collection of static configurations. He calls them nows.
And he has this wonderful, if slightly abstract analogy of Platonia.
Yes, Platonia. He asks you to imagine a vast, abstract landscape, like an infinite art gallery. Every single point in this gallery is a possible arrangement of everything in the universe.
Like a single frozen snapshot in time.
Exactly. One point over here is the universe where dinosaurs are roaming the Earth. Another point way over there is the universe where you and I are having this conversation right now. Another point is the universe where the Roman Empire never fell. Every possibility is a point in this landscape.
And crucially, all these points just exist. They aren't in a sequence. There's no line connecting them from past to future.
No line at all. They're just scattered there, like a deck of cards thrown on the floor. There's no flow from one to the next.
Okay, but then, this is the part I always get stuck on. If the cards are just scattered on the floor, why do I have a memory of having breakfast before I came here to record this?
Yeah.
Why does my brain experience a clear sequence?
Barbour has a very clever, though admittedly challenging answer for this. He calls them time capsules.
Time capsules.
Right. He poses the question, how and why can something static and timeless be experienced as intensely dynamic? His answer is that the physical arrangement of your brain in this one static flow contains structures that you interpret as memories.
So you're saying, I'm not remembering the past because it actually happened in a sequence. I'm remembering it because my brain, in this frozen snapshot of a moment, is physically wired to contain a record of a so-called past.
Precisely. Think about a fossil. When a paleontologist finds a dinosaur fossil embedded in a rock, that fossil exists now. It's a structure present in the current configuration of the universe.
It's just a rock.
It's a rock, but you interpret it as direct evidence of a past that existed millions of years ago. The fossil itself is just a static object that implies a history.
Okay, I see the analogy.
Barbour says your brain is exactly the same. Your neurons are arranged in a very specific pattern right now. That pattern contains the data you call the memory of breakfast. You experience that data as a memory of a previous event, but in his reality, there is only this arrangement.
So my memory of this morning is just a fossil encoded in my neurons at this present instant.
Yes. And because this now, the one where your brain contains these fossils, is so richly structured, it creates this powerful illusion of a history, of a flow. Barbour argues that what we perceive as the passage of time is just us occupying a sequence of these highly structured time capsule nows.
That, a lot to process. It makes me feel like I'm a single frame in a long movie reel, and I only think the movie is playing because my frame contains a detailed picture of what the previous frame looked like.
That's a perfect way to put it. The motion is an illusion derived from the correlation between the static frames, not from any actual movement through time. And it's not just Barbour thinking along these lines. Carlo Rovelli, who is a giant in the field of loop quantum gravity, also argues for physics without time.
Rovelli's the one who talks about relational physics, isn't he?
Yes. Rovelli's approach is to say we should just stop obsessing over this step variable, this idea of a universal time. He says time isn't a fundamental container for reality. Instead, we should just focus on how physical variables change in relation to one another.
Can you give me an example of that?
Sure. Usually we'd say something like, the pendulum swings to position X at time t. We use time as the master reference for everything. Ravelli says, forget t. Just say, the pendulum is at position x when the hand of the clock is at position y.
So it's just things relating directly to other things, no middleman.
Exactly. I start to feel hungry when the sun is high in the sky. I go to sleep when the sun is low. You don't actually need a hidden time variable to describe the world. You just need the physical relationship between the sun and your stomach, or the clock and the pendulum.
So in this view, time is just a useful bookkeeping device we invented to keep track of how everything moves relative to everything else.
A very useful tool, but not a fundamental ingredient of the universe. And this idea that time isn't fundamental leads us perfectly into the frontier section, because if time isn't in the basement of reality, then it has to be emergent.
Emergent, okay, like how the property of wetness isn't something a single water molecule has.
Exactly.
But if you get enough of them together, the collective behavior we call wetness emerges.
That's the perfect analogy. Or how heat is really just the average motion of atoms. The atoms themselves aren't hot or cold. Their collective movement emerges as temperature. So the billion-dollar question on the frontiers of physics is, what is the microscopic motion that emerges as what we experience as time?
We have some seriously wild theories here in the stack. The first one you flagged is the Page-Wooders mechanism. This goes all the way back to a 1983 paper.
It does. It's a beautiful and elegant idea proposed by Don Page and William Wooders. And it's a direct attempt to solve that Wheeler-DeWitt problem, the problem of the frozen universe equation.
So how do they unfreeze it? If the universe is static, how do they get change to happen?
They do it with quantum entanglement. So they start by accepting the premise. Let's say the entire universe as a whole is in a static state. It's a frozen block. It doesn't change over time.
Okay, we're back in the block of ice.
But now suppose you split the static universe into two parts. You can draw the line anywhere you want. You call one part the clock and the other part the rest of the world.
Okay, a clock and a world.
And here is the absolute key to their idea. The clock and the world are quantumly entangled with each other.
Entanglement. That's the spooky action at a distance where the state of one particle is instantly correlated with the state of another, no matter how far apart they are.
Exactly. So even though the whole combined system is frozen and timeless, if you are an observer living inside the system, you can look at the clock and compare it to the world.
And see your relationship.
You see a correlation. You see that when the clock is in state A, the world is in state B. And when the clock ticks to state C, the world is now in state D.
So the evolution, the passage of time, is nothing more than the correlation between the parts of the static whole.
Yes. Let's use another analogy. Think of a book sitting on a shelf.
A physical book, huh?
That book is a static object. It just sits there. The whole story, from page 1 to the end, is already written and exists all at once. Nothing is happening.
Right, it's a block of paper.
But if you open it, what do you find? You find a correlation between the page number, which we can call the clock, and the words on the page, which is the system.
Page 10 describes the hero leaving their village. Page 200 describes the hero fighting the dragon.
Exactly. The book as a whole exists all at once. But for the reader, the internal observer, a story evolves as they correlate the ticking of the page numbers with the changing state of the narrative. The Page-Wooders mechanism suggests time is that entanglement between the page number and the text.
And there have been actual experiments testing this recently. We have a source here from Medium and ArcSviv talking about a quantum experiment that shows how time emerges from entanglement.
They actually built this in a lab.
Well, they simulated it using photons. It's fascinating.
Tell me more.
They created a static global state using entangled photons. From the perspective of an outside observer measuring the whole system, nothing changed. The state was static, just like the Wheeler-DeWitt equation says.
It's the frozen universe.
But for an internal observer, which they simulated by measuring one photon relative to the other time, appeared to flow, the polarization of one photon would change in a predictable way relative to the clock photon.
That is absolutely incredible. So time is literally a matter of perspective. From outside the universe, it's a static block. From inside, it's a story unfolding.
And it's a story whose coherence comes from quantum entanglement.
But that's not the only idea out there. There's another hypothesis in our stack that connects time to something even more familiar: heat.
Right. The thermal time hypothesis. This is where we get the Kess phrase. Temperature is the speed of time.
This idea comes from Carlo Rovelli again, working with the mathematician Elaine Kohn. And their argument is that time is, at its core, ignorance.
Ignorance. How so?
It's all about a concept called coarse graining.
Coarse graining. Like a blurry picture.
Exactly like a blurry picture. Let me ask you, what is heat? If you could look at a glass of hot water with a super powerful microscope, would you see little hot water molecules?
No. I just see molecules zipping around really fast, bouncing off each other.
Exactly. You'd see position and velocity, you'd see individual particles doing their thing. At the most fundamental microscopic level, there's no such thing as temperature. Temperature is a macroscopic concept. It's what we feel because we can't track every single one of those trillions of molecules. It's a statistical average of their motion.
Okay, I'm with you. Heat is just a blurry summary of a lot of microscopic motion.
Ravelli and Cum argue that time is exactly the same thing.
A blurry summary of something more fundamental.
Think about it. If you were some kind of super being, a Maxwell's demon, who could see the exact position and momentum of every single particle in the universe all at once, you wouldn't need time. You'd just see the complete static state of the universe. The flow would disappear because you'd see all the microscopic details that, for us, are hidden.
Because I'm not a demon. Because I'm a limited human being.
Because you are human and your perception is coarse-grained, you're seeing the blurry, averaged-out picture. You can't see that fundamental microstate. You only see the average behavior. And the laws of statistics, of thermodynamics, imply that this average changes in a very specific direction.
The arrow of time. The move toward higher entropy.
Yes. We perceive time flowing forward for the same reason we perceive a cup of hot coffee cooling down to room temperature. It's just the most statistically probable outcome. If we knew everything, the past and future might look identical, but because we are ignorant of the micro details, we perceive a flow from order to disorder.
That is an incredibly humbling thought. You're saying that the passage of time isn't a fundamental law of the cosmos. It's just a side effect of my own limited perception.
Ravelli calls it thermal time, and it gets even spookier and more personal when you bring in a concept from one of the papers called the diamond.
The diamond. This was in that paper called Diamond's Temperature, the one about our finite lifetimes.
Yes. It gets into the geometry of our existence. Imagine your life from the moment of your birth to the moment of your death.
Right.
In physics, we can draw what are called light cones. There's a light cone expanding forward from your birth, representing everything you can possibly influence. And there's a light cone contracting backward to your death, representing everything that can possibly influence you. The intersection of those two cones forms a diamond shape in space-time.
And that diamond represents everything I can possibly see, touch, or interact with during my entire life.
Correct. Anything outside that diamond is causally disconnected from you. You have a horizon, just like a black hole has an event horizon.
I have a personal horizon.
Yes. You cannot see beyond your death. You cannot know what happens before your birth. Information is fundamentally hidden from you. And in physics, a fascinating thing happens whenever you have a horizon where information is hidden.
You get a temperature.
You get a temperature. This is the same principle behind Hawking radiation. A black hole has a temperature at its event horizon because we can't see what's happening inside. The thermal time hypothesis suggests that you, Andrew, have a temperature associated with your life simply because you can't see outside your own lifetime.
Wait, just by being mortal, by having a beginning and an end, I am generating a thermal bath for myself.
That's the theory. The paper actually derives a formula for it. For an observer with a lifetime of T, there is an associated temperature. It's a tiny number, but it's not zero.
So TD equals 2 bar pi kBT.
That's the one. And the takeaway is just profound. The fact that we are mortal, the fact that our time in the universe is finite, is what creates the thermodynamic conditions that give us a sense of time in the first place. If we lived forever, or if you could see the whole block at once, this thermal time might just vanish.
That's almost poetic. Our mortality creates our experience of time.
It ties the observer to the physics in a really deep, fundamental way.
And there's just one more frontier idea mentioned in the notes. Something about holographic spacetime.
Yes, we should touch on that briefly. It's the idea that the 3D space and 1D time we experience might actually be a projection, a hologram generated by quantum information living on a lower dimensional surface at the boundary of the universe.
So it's basically the Matrix.
In a highly abstract mathematical sense, yes. It reinforces this general theme that space-time isn't the fundamental stage on which reality plays out. It might be an emergent property of something deeper, like quantum entanglement.
Okay. My brain is officially melted.
Mm-mm.
We've gone from a simple river to a loaf of bread to a deck of scattered cards to time being an emergent property of heat to the whole thing being a hologram.
It's a wild ride.
But we still have to get up tomorrow. We still live our lives. So let's bring this back down to earth. Let's talk about the implications. How does all this physics actually land in the real world? And I want to start with the brain.
Okay.
If time at the fundamental level is this chaotic quantum fog or a static block, why does my experience of it feel so smooth and continuous? Why does it feel like a seamless film and not a series of snapshots?
This is where neuroscience comes in. We have a great source from Polytechnique Insights that looks at how the brain actually constructs our perception of time. And it turns out your brain is a fantastic film editor.
It's all done in post-production.
A lot of it is, yes. Your brain doesn't actually process information continuously. It seems to process it in discrete little windows, often correlated with what are called alpha waves. These windows are about 80 to 100 milliseconds long.
So we're basically seeing life in frames per second, like a camera.
Roughly 10 to 12 frames per second, yes. Your brain takes all these discrete snapshots from your senses: vision, sound, touch, which, by the way, all arrive at the brain at slightly different speeds, and it masterfully stitches them all together into a single coherent story of now.
So the smooth flow is an illusion created by my brain's editing software.
It seems to be, and this also explains subjective time dilation. You know how people who've been in a car accident often say that time seemed to slow down?
Yeah, that everything went into slow motion. I've heard that a lot.
The laws of physics didn't change during the accident. Your brain just went into overdrive. The research suggests that during moments of intense fear or emotion, the brain's processing density ramps up. It starts taking more snapshots per second.
So when I play the tape of that memory back in my mind, there are more frames packed into that 1 second, so it feels like it lasted longer.
Exactly. It's not the physics of the universe that changed. It's the editor in your head that changed the frame rate to maximize your chances of survival.
Okay, but that brings us to the big one, the one that really keeps me up at night when I think about this stuff. Free will.
The elephant in the room of the block universe.
If we live in a block universe, and the future already exists, if that alien in Andromeda can already see what I'm doing next Tuesday, then isn't the script already written? Am I just a puppet acting out lines that were determined at the Big Bang?
This is a massive philosophical and scientific debate. One of our sources, the physicist Marina Cortez, argues very strongly against the block universe for this exact reason. She champions what she calls a becoming universe.
She's trying to save free will.
She is. She argues that new events must be genuinely created in the present. The future is not fixed. She believes the block universe view turns us into puppets reading a script, and that physics must find a way to account for the genuine creation of novelty in the universe.
I have to say, I'm on her team. I want my choices to matter. I want to believe I'm creating my future, not just discovering it.
I think we all feel that way, but there is a powerful counter view. It's a philosophical stance called compatibilism. It argues that even if the block universe is real, even if the future is fixed, it doesn't eliminate free will.
How is that possible? If the outcome is already determined, how can my choice be free?
The argument is that you are the mechanism that determines it. You aren't a puppet watching the script. You are the character acting out the script through your choices.
But if the script is already there,
it's there because of the choice you are going to make. Your decision-making process is part of the physics of the block. The block contains your brain weighing options, your neurons firing, and you ultimately making a choice. The future is determined, yes, but it's determined by your choices, among many other things.
so my deliberation is real and my choice is real, but the outcome of that choice is already a fixed feature of the four-dimensional block.
Precisely. You can't just sit back and say, well, the future is fixed, so I'll do nothing, because if you do that, the block will simply contain a future where you did nothing. Your choices are the causal link that cements the future into the block. You are a necessary part of the process.
That's a real brain twister. It's a subtle distinction, but I think I can live with that. It's better than being a mindless robot.
And you know, there's actually a beautiful and I find quite comforting philosophical upside to this block view, especially to Julian Barber's Platonia idea.
And that would be the idea of living in the now.
Exactly. If you believe time is a river, then life is fundamentally tragic. It's defined by loss. Every moment that passes is gone forever. The past washes away. That perfect moment you treasured, holding your child, a wonderful meal, a beautiful sunset, it's gone.
Like tears in rain, as the line from Blade Runner goes.
A perfect quote for it. But in Barber's view, in the view of the block universe, nothing is ever lost.
Because it's all just another point in the infinite gallery of Platonia.
Every moment exists eternally as a coordinate in reality. That Tuesday afternoon from your childhood when you felt perfectly happy, it's still there. It's a real place in space-time. It is just as real as this moment right now.
There's that lovely anecdote in the source material about the opera singer Dame Janet Baker.
Yes, Barber cites her. She said she never listened to her past recordings. She believed the now is what is real. She approached every performance as if it were a completely new, spontaneous event existing only in that moment.
But from Barber's perspective, every one of those performances exists forever as a perfect, timeless now.
Exactly. And this view encourages a profound philosophical shift. Instead of mourning the passage of time and the loss of the past, you can learn to appreciate the incredible richness of the current configuration, the current now. You aren't losing moments, you are simply visiting them as you traverse this vast, timeless landscape of reality.
That is actually quite comforting. It makes the now feel heavier, more significant. It's not some fleeting bridge between a dead past and an unborn future. It's a destination in its own right.
The now is what is real.
There was one last thing in the implication section, a quick note on AI and consciousness.
Right. It's an interesting question to consider. We build our AI on computer clock cycles. They operate on a rigid, discrete, step-by-step version of time, tick-tock compute.
So does an advanced AI feel the flow of time the way we do?
The research we looked at suggests there's a key distinction between algorithmic machines that just process sequential data and the way biological brains consciously process temporality. We stitched together that illusion of flow for evolutionary and survival reasons. An AI might just see the block of data for what it is without the river-like illusion we experience.
So maybe an AI would see the universe more like a physicist does.
Perhaps. In a strange way, they might be the true native inhabitants of the block universe.
Wow. Okay, we have covered a staggering amount of ground.
We certainly have.
Let's just try to quickly recap this entire journey. We started with the comfortable idea of time as a river, our basic intuition. Then we moved to Einstein's block universe, that loaf of bread where the future already exists.
Then we saw that block dissolve into a quantum fog with the Wheeler-DeWitt equation, where time vanishes from the math entirely. We saw Julian Barber rebuild the universe as a collection of static now cards.
And then we watched time re-emerge, like heat from a coffee cup, generated by our own ignorance in quantum entanglement. We even learned that our own mortality might be the very thing that gives us a temperature and therefore a sense of time.
And finally, we saw how our brains, these amazing editors, stitch all of that underlying chaos into a coherent, flowing story. And how, even in a frozen, predetermined universe, our choices might still be the most important things in it.
Whether it's fundamental or an illusion, time is the medium in which we live our lives. It's the water we swim in, even if that water is made of, well, some very strange quantum math.
As Einstein said, it's a persistent illusion, but a very, very convincing one.
And maybe, if Julian Barber is right, we should stop worrying so much about the river washing us away and just take a moment to enjoy the incredible view from wherever we happen to be standing in the gallery.
I think that's a beautiful way to end it.
Before we wrap up, thank you to all our partner sponsors and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.